Hello everyone, my name is Shang. It's my pleasure to be speaking with all of you here, and the topic of my report today is a mechanistic understanding of coupled transport phenomena for visual design of solar interfacial equation device. My presentation includes the following three parts, and the first part is about the research background. The increasing continuously of freshwater demand make a shortage of freshwater resource became one of the most serious global problems, and due to the fossil energy crisis and abundant solar energy resources on the Earth, seawater desalination by solar energy is regarded as one of the most promising ways to produce fresh water. The efficiency of traditional producing freshwater strategy by solar energy is low because of the heat loss, such as direct heating backwater, putting absorber at the bottom, and suspending nanoparticles in water. In recent years, the solar interfacial evaporation technology begins to catch our eyes. A typical solar interfacial evaporation system consists of two layers: the absorption layer, which was used to absorb sunlight and transferred it into heat, and the insulation layer, which is used for insulation and pumping water. The advantages of the solar interfacial evaporation system compared with the traditional method include the efficient light-to-heat conversion, good thermal management, and the high evaporation efficiency. At present, the developed status of this technology is that various materials and structures are used and developed to improve the evaporation efficiency, while there is no detailed theoretical model to guide the engineering design and no clear definition to distinguish what is the interfacial evaporation and the volumetric evaporation. This is the energy analysis for the solar interfacial system. The sunlight enters the system from the top surface. Part of the energy is used for evaporation, and the rest of the energy is lost from the top, side, and bottom of the system. It mainly includes the heat conduction, heat convection, and heat radiation. The evaporation rate and evaporation efficiency are the two key parameters to evaluate the evaporation performance. The evaporation rate is defined as the evaporation mass loss per unit area per unit time, and the evaporation efficiency is the ratio of the energy used for evaporation to the total energy incident in the system. The second part is about the model developing. The geometry of the model including the ambient, the evaporator, that is the absorption layer, and the insulation layer, and the bulk water, and the geometrical parameters are shown in this table. The model was solved using the console multiphysics 6.0 for the physical field. The laminar flow part was used to calculate the velocity and pressure of the ambient, and the transport of diluted species part was used to solve the vapor concentration in the environment, and the heat transfer part was used to calculate the temperature distribution of the whole region. For the radiation in participating medium part was used to solve the light absorption and the radiation transferred in absorption layer and the insulation layer. And the energy balance model with gravity was used to solve the waterfront in the evaporator. This is about the boundary condition for different physical fields. The third part is about the validation experiments. After getting the model, we designed a symbol validation experiment. The first session of the experiment is about the preparation process of the symbol, which is combined with carbon particles for the absorption layer and the cellulose sponge for the insulation layer. And the final symbol was called the C-sponge for short, and the specific parameters are listed here. Then we measured various parameters, for example the pore size distribution, which was obtained by processing SEM picture with imaging software. As we can see, there are dual scope of pore size in cellulose sponge, which are the millimeter and micro-sized pores. The dynamic contact angle was also tested. Microscopically, it shows that the level rises rapidly in the symbol, and as a result, the change of waterfront height with time and the wicking rate at each waterfront height can be obtained. Next is about optical parameters for sponge and sea sponge. The reflectance and transmittance of the sponge and the sea-sponge can be measured by the spectrophotometer directly, and according to the characteristic of light absorption, the absorption efficiency of the symbol under a solar spectrum can be obtained, and also the absorption coefficient can be calculated according to the Beer-Lambert law, and these parameters would be used for the model developing. This is a summary of all measured experimental parameters. The parameters written in dark green are used for the model, and the orange part are the results, which are waiting for validation with our model. The evaporation rate and evaporation efficiency can be calculated by this equation. The results for experiments and simulations are shown here, and the shaded part in the figure is the experimental data. The results error of the evaporation efficiency and the evaporation rate between the experiment and the simulation are controlled within only 1% under steady-state condition. The last part is about the results. Firstly, the interfacial location and the interfacial thickness is defined here according to the temperature distribution in the evaporator. The interfacial location is the location of the cross-section with the highest temperature in the system, and the interfacial thickness is the height of the region in which superheat is larger than 10%. The superheat here refers to the temperature difference between the highest temperature in the system and the far-field ambient temperature, and the height of the waterfront is the exact liquid height in the system where the wicking rate is equal to the evaporation rate. This part shows the effect of absorption coefficient and thermal conductivity on the evaporation efficiency, and the corresponding interfacial location, interfacial thickness, and light absorbing distribution are also shown here. Three regions with distinct evaporation behavior were identified. The region 1 is the volumetric region, region 2 is the transitional region, and region 3 is the interfacial region. For the region 1, due to the small absorption coefficient, the interfacial location is located at the bottom surface of the system, so higher thermal conductivity led to the higher evaporation efficiency due to a decreased heat conduction loss. And as for region 2 with the increased absorption coefficient, the light is absorbed within the evaporator. The interfacial location is in the middle of the system, and The larger interfacial thickness indicated that the temperature distribution in system is uniform. So with the increase of the thermal conductivity, the evaporation efficiency decreases, which was reversed compared to the region 1 due to the increased heat conduction and the decreased heat convection and heat radiation. In region 3, the efficiency is in general insensitive to the variation of the thermal conductivity. This is because that larger thermal conductivity will lead to the increased heat conduction, while it will also cause the reduced the heat convection and heat radiation. And then the effect of kinetic angle, which could tune the interfacial location, and the absorption coefficient, which could tune the waterfront, on the evaporation efficiency is shown here. Two regions, which are the full region and the half-full region, are also identified according to the waterfront height and in the evaporator. For the full region, the evaporation efficiency is not sensitive for the variation of kinetic angle, as the waterfront is always at the top surface of the evaporator. But there is an optimal absorption coefficient for each kinetic angle to minimize the heat losses to achieve the maximum efficiency. For the half-full region, the interfacial location, interfacial thickness, and waterfront height can be effectively tuned by absorption coefficient and water kinetic angle. The optimal evaporation efficiency could be found at theta is equal to 89.85 and the absorption coefficient is equal to 200 per meter due to the decrease in heat radiation loss and heat convection loss. This is because the best match between the waterfront and the interfacial location and the interfacial thickness. Last, we make a summary about our presentation. Firstly, we developed a comprehensive 2D multiphysics model accounting for the optical, heat, and mass transfer involved in a solar interfacial evaporation system. And then experimental validation was made, and the results error of the evaporation efficiency between the experiment and the simulation is controlled within 1%. And thirdly, further improvement of the evaporation efficiency can be achieved by dedicated the design optimization for optical absorption and thermal conductivity to control the interfacial properties. And last, the maximum evaporation efficiency can be obtained by tuning the kinetic angle and the absorption coefficient to make the best match between the waterfront and the interfacial location and the interfacial thickness. That's all. Thank you.